Hello, everyone, and welcome. So this is going to be a lecture for my game theory class, which is Economics 318. So the focus of this lecture is going to be on repeated games. So this is chapter 13 in our textbook, if you want to refer to that for some more information. So the motivation here is that all of the games that we've looked at so far, we play a game with someone and then that's it, right? So we never see them again. So the idea is, that's the sort of simplest case, so that's what we start off with. But what we want to do now is to expand on that idea and say, hey, in the real world, a lot of times you're going to see someone, have some kind of interaction with them, and then you're going to see them again down the road. So that's going to be true whether we're talking about people playing a game, whether we're talking about businesses having some sort of interaction, or say governments having some sort of interaction. All of these games are going to be, in some sense, repeated. Okay, so we're going to focus a lot of our attention when we talk about repeated games. We're going to focus a lot of our attention on the prisoner's dilemma. So here's just like a regular one-time prisoner's dilemma that we've seen a bunch of times in this class. So we're going to have player J, player K. They can each cooperate or defect. Payoffs, if they both cooperate, are pretty good. If they both defect, are pretty bad. If one player cooperates, so J cooperates and K defects, then it is a disaster for J. So we'll say -3 and 2. Okay, so that's just our regular prisoner's dilemma. So hopefully you all remember or can sort of convince yourself that, for example, D is a dominant strategy for J. And of course for K as well. And I guess we may as well talk about why that is, because like I said, we're going to be talking about prisoner's dilemma quite a lot. So if if K plays C, then J could get 2 by playing D, and J could get 1 by playing C. And so then also, if K plays D, then J is choosing between getting 0 by playing D and -3 by playing C. So D is dominant strat for J, and of course, also for K. Okay, great. So we have the single, sort of the one-time game of Prisoner's Dilemma. That's sometimes called a one-shot game. So the one-shot Prisoner's Dilemma, we have a dominant strategy for each player. And so if we have a one-shot Prisoner's Dilemma, then we as economists can feel pretty comfortable saying we predict that the outcome will be D. Okay, so the reason that we're interested in this, and the reason that we're interested in talking about the prisoner's dilemma in particular, is this is kind of a bad outcome, right? So if they play DD, then they'll both play D, they get a payoff of 0 and 0. If they both played C, then they would get a payoff of 1 and 1. And so, if these players are in an environment where they can just write a contract, then the solution is really easy, right? So they write a contract. It says, yes, we're both going to play C. Anyone who violates that has to pay $1 million. Great. And then we both play C. So what we're thinking about is, cases where that's not possible for whatever reason. So it could be 2 countries are doing something. It could be, say, 2 criminals are doing something and don't necessarily want to get the courts involved to enforce contracts. So for various reasons, these contracts are not available. And so what we're interested in is, well, maybe if we can just let these 2 players play a bunch of times, then maybe that will have some sort of different impact. And maybe we'll be able to end up just playing CC if we have a structure where the two players are going to play more than once. Okay, so let's try this. So suppose they play twice. Well, we need to figure out, or we need to establish how the players, how do the payoffs work if they're going to play twice? So what we're going to assume is payoffs for the whole game well, we're just going to make the sort of simplest assumption for right now. So payoffs for the whole game are the sum of the two payoffs. So, one way that we can write that in symbols would be, so J's payoff is equal to J's payoff the first time they play Prisoner's Dilemma plus J's payoff the second time they play Prisoner's Dilemma. And of course, the same analogous thing for player K. Okay, so let's look first for Nash equilibria. Well, actually, you know what? Before we start looking for Nash equilibria, let's back up 1 second and just talk about what a strategy means in this case, right? So an example of a strategy for J would be something like this. So here would be a strategy for J. J could say, well, in the first period, I'm going to cooperate. So in the first period, I'm going to cooperate. And then in the second period, it's going to depend. So I will cooperate if K played cooperate in period 1. And then otherwise, I'll play D. So this is the second period if K played D in period 1. So this is just an example of a strategy for K. For J. So the point is we need to specify fully what J is going to do. And remember that may depend on what K did. So here's another strategy. For J would just be defect, 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 defect. So this would just mean J's going to play D no matter what. J will always play D. Okay, so I'm going to try to keep this in sort of short chunks. So I'm going to take a break here, and we'll pick back up in just a moment.